Okay, guys, sorry about class today. Was not expecting to have to cancel, but that's all right. We are going to finish up 2.1. So 2.1, remember, we're talking about second order differential equations, and we proved at the end of class, right? We proved, let me get rid of that. Oh, whoops. Come on. At the end of class, we proved last Thursday the existence and uniqueness theorem. Oh, no, not that yet. Sorry, I'm on the wrong page of my notes. Just the theorem that if, so remember, if I have a linear differential equation of this form, where P and Q are functions of X, right? Then I know that if Y1 and Y2 are solutions, right? Then this implies that the general form y equals c1y1 plus c2y2 is also a solution. So that's going to be kind of what we want to do in this section. We're going to look at an existence and uniqueness theorem, and we're going to talk about solving initial value problems, and then we'll actually talk about how do we solve some specific type of second order linear. So really quick, I just want to show you an example. Let's consider the differential equation y double primed minus y equals 0. Then you can check for yourself that one solution to this differential equation would be e to the x, and another solution to this differential equation would be e to the negative x. And sure enough, you know, if you took the second derivative of e to the x, you would get e to the x minus e to the x is 0. Second derivative of y sub 2 is e to the negative x minus e to the negative x is 0. So again, what does this equation right here tell us then? That y, if I have y equals c1 y1, which is e to the x, plus c2 y2, which is e to the negative x, that tells us that that is a solution. And so how can we check this? I'm going to start with one side of the equation. So what would the second derivative of this be? Well, y primed would be c1 e to the x minus c2 e to the negative x. And y double primed then obviously is c1 e to the x now plus c2 e to the negative x. So clearly when I take y, I get c1, excuse me, e to the x plus c2 e to the negative x. And I'm going to subtract y double primed, which obviously, right, obviously is 0. Okay, so we've shown then that for some constants c1 and c2, this form right here is going to be a solution also. And you can see this gives us a lot of different forms, right? Because I can change c1, I can change c2, and then I would add those together. So the interesting thing with the second order, and this kind of makes sense, is if I want to find a particular solution where I know what c1 is, I know what c2 is, then I would have to have sorry, there's a lot of noise outside of my office here. I would have to have some conditions. And so now, because I have a double primed, I don't just need one initial condition. I'm going to have more than one initial condition. I'm going to have like 2 values for this to work. Okay, so before we do an example of one with the 2 values, what we need to know this idea of existence and uniqueness, and when are we going to have a unique solution for different initial values. And this existence and uniqueness theorem is quite a bit easier than the other one that we have had before, where we had to have these partial derivatives. This one, I just need some continuity, people, and that's it. So existence and uniqueness. So a couple things. Let's set this up as normal. So here's what we need. Let's let P, Q, and F be continuous functions on an interval. Let's get crazy. Let's call it I, which contains A, containing some x value A. All right. Then given numbers, so I need 2 numbers. And let's just call those B0 and B1. The equation, the differential equation, we'll just say the equation. All right, so the second order linear differential equation, I don't need it to be homogeneous now, equals f. So this just tells us more about existence and uniqueness. We're going to deal, of course, with homogeneous for a while, but this guy has a unique solution on the entire interval I. So this is pretty awesome. I know you think it is too. And the solution, it's a solution that satisfies, whoa, hold on, spelling, right? Satisfies the initial conditions, y of a equals b naught, and my other initial condition, y primed of a now equals b sub 1. So this existence and uniqueness theorem is quite a bit more lenient than the one that we've dealt with before. All I need is continuity of these three functions right here, and we're going to be good to go. Okay, so let's look at an example of this. You can, I know I go too fast, I know you guys get me at going too fast, but the lovely thing is now, whoops, hold on. The lovely thing is now you can pause me or fast forward me. Maybe you care more about fast forwarding me than pausing me. So let's do an example here. Let's look at that other example that we had, y double primed, not plus, minus, oh, come on, minus y equals 0, where we know a couple things here. Let's say that y of 0 equals 3 and y primed of 0 equals 7. So in this case, if you think about this, what are our functions out here? Well, I don't have any function here, that's okay. But what is my function in front of y? It's -1. So I know in some interval around -1, I'm going, or sorry, some interval around 0, excuse me, this sucker is continuous. Not just some interval, it's continuous everywhere around 0. So we know that we're going to have a solution that exists on this entire interval, basically the whole real number line, which we know is true. And remember, we know that y sub 1 is e to the x, and y sub 2 is e to the negative x. So I know one of my solutions, or a general solution, we haven't talked about does this represent all the solutions, but we will. All right, so how am I going to find this? So what do I know? I know that y of 0, which is c1 e to the 0 plus c2 e to the 0 must equal 3. So what does that imply? That I have c1 plus c2 equals 3. So I also know y primed of 0 is 7, so I'm going to need y primed. So y primed here is c1 e to the x minus c2 e to the negative x. So I'm going to use that fact then, that the derivative, when I put in 0, oh, that's not a plus. Whoops. That's a minus. c2 e to the negative x equals 7. So that implies, because e to the 0 is 1, I get c1 minus c2 equals 7. So when you're solving these, there are a couple ways you can do this. If you remember, this is kind of college algebra stuff, solving two equations with two unknowns. You can, you could solve this equation maybe for c1 and then plug it in here. We could add these. When I look at this right away, because I see the c1 and c2 have opposite signs, I'm just going to add these two equations. So I get 2c1, and then c2 minus c2 is 0, and 3 plus 7 is 10. So c1 then equals 5, and then if I plug that back in here, it looks like c2 is -2. So what is my particular solution then? It's going to be 5 e to the x minus 2 e to the negative x. This is going to, so if you think about what this is the solution that will go through the point 0,3, and not only will it go through the point 0,3, but the slope, right, of the graph at 0 is going to be 7. So you can see how there's a lot of ways we can change this, right? We can change the slope of the graph at that initial value. We can change where the actual point is. Lots of different ways that we can deal with this. One thing I do want to comment about here, if those of you have had linear algebra, we talked about this, those of you have had me for Calc 3, we could put this into a matrix, right? Solve 1, 1, 1, negative 1, 3, 7. I am fine with you doing that. If you have no idea what I'm doing and you're wondering what is this magic that she speaks of, just let me know. I can show you how to do that. You're welcome to do a matrix. Just maybe give me a note somewhere that says, you know, calculator, or I did this in a matrix, or just show me maybe the setup of the matrix or something, so that I can, of course, give you partial credit if something goes wrong. But I hope that makes sense. Okay, so I was talking a little bit about, let me clear this out. You know, how can I really call, when I look back here, can I really call this guy right here my general solution? Meaning, does this really encompass all the possible solutions, or could I find, you know, 2 other ones like this that I would be able to put in there and it still work? So the interesting thing is we're going to see that that really is the general solution. That gives us all of the possible solutions. So before we get there, though, we need a definition. And the definition that I need is this idea of linear independence. So those of you who have had linear algebra already know what I'm talking about. Those who have not, oh, I'm so excited for you to someday have it. But let's write down this definition. 2 functions defined on an open interval. So I'm just going to put, well, I should probably be good. Whoops. Defined on an open interval. I don't know, let's call it I, like usual. We say are linearly independent. All right, so if you've had linear algebra, you know what linearly independent is. And if I wasn't talking to a computer, I would ask you to tell me, but nope, I'm not there. So I'm talking to a computer. You can tell that I'm super happy about canceling class. Anyway, it's fine. All right, so 2 functions defined on an open interval I, or what we say linearly independent on I, provided that neither is a constant multiple of the other. So those of you that have had linear algebra, remember if we have 2 vectors, that is one way that we can determine if they're linearly independent or not, is see if they're constant multiples of each other. If we have more than 2 vectors, remember we just can't write it as a linear combination of the other 2. So linear combination is just adding up things with constants in front of them. But this is what we mean to be linearly independent, okay? So a couple notes here. Linear dependence, or linearly dependent then, what would that mean? Linearly dependent means we can write f as a, I'm just going to use f here, constant multiple of g. So that's an example. And in this case, if we can write f as a multiple of g, then this is kind of interesting, because then this implies that if I take like f, well, let me back up a little bit. One way we can test this is if they are linearly dependent, then that means f equals some constant times g, or vice versa. So what this means is if I take the fraction or the ratio of these guys and it equals a constant, then that means that I am linearly dependent. Okay, they are not linearly independent functions. So what do I want to show you? So let's look at some examples here of linear independence or linear dependence. Okay, and then we'll talk about like how maybe we can figure that out. So for example, you know, if I look at the function f of x equals e to the x, the one we've just been doing, and g of x equals e to the negative x. So obviously, right, these are not linearly dependent, because I cannot write one in terms it's a multiple of the other. So for example, if I tried this, you know, f over g kind of jazz, e to the x over e to the negative x equals e to the e to the 2x, which clearly is not a constant, right? Same thing with, you know, sine and cosine. These guys are linearly independent. Sine of x, g of x equals cosine of x. One is not the multiple of the other. Now, an interesting one, so obviously like 4x squared, right, and 3x squared are clearly linearly dependent. The reason I can see that is if I divide them, 4x squared over 3x squared, I get a constant, okay? Linearly dependent, okay? Let me show you one other one really quick. Get rid of some of this. You already have that down, right? I don't know. I'm not just going to the next page because I don't feel like it. All right, and so let me show you one really quick where they are linearly dependent, but it's maybe not so obvious. So one that I always kind of forget about is if we have f of x equals, let's say, sorry. So like, let's say we have sine of 2x, and let's say g of x equals sine x cosine x. So this one might look like they are not linearly dependent. However, as you remember, I know you do, what is the formula for sine of 2x? This is the double angle formula. This is 2 sine x cosine x. So this one's a little bit tricky because if you see, this f is actually just a multiple of g. So these guys are linearly dependent. Okay, so those are just some examples of linear independence and linear dependence, okay? Good. So what does that have to do with solving these differential equations? Well, what we're going to find is that, so we had those, oh, did I erase it? Oh yeah, okay, so we had this y sub 1 and y sub 2. What we're gonna find is if this y sub 1 and this y sub 2 are linearly independent, meaning I can't really write one in terms of the other. That's kind of the idea of linear independence. If these two are linearly independent, then what we're going to see is that this solution right here is not only a solution to this differential equation, it is a general solution to the differential equation, okay? And that's a pretty big deal because that means we can get everything. So before we do that, there's one other example of well, not one other example. There's one other way that we can try and test linear independence without maybe having to see, you know, if you don't remember maybe the double angle formula for sine, is there another way that we can do this? And we can. And it's going to be with something called the Ronskian. So you've probably heard about this. I'm sure at all your cool parties you've heard about it. So given f and g, all right, then we're going to define the Ronskian. The Ronskian, that's just a cool word, period. And the Ronskian is going to help us see if two functions are linearly independent or dependent, just based, you know, if it's not as easy as just looking at them and seeing, oh yeah, this is the double angle formula. If we took the Ronskian of these two, we'd be able to for sure say this is linearly dependent, okay? So the Ronskian of f and g is the determinant as follows. Okay, so the determinant, the Ronskian is, here's what we're going to have. We're going to have f, g here, and we're going to have f primed, g primed here. Okay, so this is called the Ronskian. You guys remember determinants. I'm sure most of you have heard of them, even if you haven't had linear algebra. The determinant, you take the main diagonal, product of the main diagonal minus the product of the off diagonal here. So this would be fg primed minus f primed g, okay? And what this does for us is it shows, and there are a couple things. Well, we're going to define this first, and then I'm going to talk about a theorem. But if you look at, before I get there, where does this kind of Ronskian come in? Well, think about if you had y double prime plus py primed plus q equals, you know, whatever, some function, okay, and I have two solutions, and I know that y of a equals b naught, and I know y primed of a equals b1. And remember, I have this y equals c1 y1 plus c2 y2. And what I'm trying to figure out is, are y1 and y2 linearly independent? Well, remember, we took the derivative, right? c1 y1 primed plus c2 y2 prime. This was that example that we did. And if I use my initial conditions, look at what I'm going to get. I'm going to get c1 y1 of a plus c2 y2 of a equals b naught. And then I get this c1 y1 primed of a plus c2 y2 primed of a equals b1. And remember that magic I did with that matrix before? That's kind of how we would solve this matrix. We'd create a matrix with this, right? Where what would we really have? We'd have this y1, y2, y1 primed, y2 primed. Those of you who have had linear algebra, you know you can multiply this by c1, c2, and this would equal the b naught b1. But the key is, this is kind of where the Ronskian comes in. And I'm sorry if I'm being a little vague about that, but we just don't have a whole lot of time to come into it. But this is basically the Ronskian right here. And if we can find that the determinant is not 0, then we have shown that it is, that these functions right here are linearly independent, okay? So they're linearly independent. We're not going to get any free variables, stuff like that for those my linear algebra folks. I'm sorry, I keep calling, talking about my linear algebra folks. But that's kind of where the Ronskian comes in. So let's bring in a theorem really quick. Let me get rid of all of this. Oops, sorry about that. All right, so here's the theorem that's going to actually be what we want with the Ronskian. Okay, so I'm gonna write this down and then we're gonna do some examples. All right, so theorem, let get some setup here. y1, y2 be solutions of the differential equation y double primed plus py primed. Oh my goodness, what are they doing outside of my office? I wonder if you guys can hear that. Oh, sorry, I need a y in there, don't I? I think you probably can. It's like it's a cart. Probably taking food somewhere. Ooh, have I forgotten that y before? Sorry. On some of our other stuff, don't forget that y. All right, let's say equals 0. Okay, so we're going to talk about the homogeneous one. Be solutions on an open interval, right? And let's let P and Q be continuous. So we know solutions exist. We want that to happen, right? If I'm going to talk about this, then we want solutions to exist. Okay, then the Ronskian, okay? So a couple things here. If y1 and y2 are linearly dependent, okay, linearly dependent, then what we're going to see is that the Ronskian of these is exactly 0. Or sometimes we'll say identically 0, or sometimes we have these 3 equal sign right here that it's identically 0. I know that's kind of weird, but that is identically 0. It's not just 0 for some t, it's 0 all the time, or it's 0 for some, it's a 0 no matter what x is. If y1 and y2 are linearly independent, then we know the Ronskian is not 0. Okay. So this is, again, one way that I can test these guys. And again, why are we doing this again? Because if I can show, the whole idea here is if I can show that these suckers right here are linearly independent, then I know that that y equals c1 y1 plus c2 y2 is the general solution, or a general solution to my differential equation, okay? So let's look at some examples really quick. Really quick, let me show you why. If they were linearly dependent, right? So if y1 and y2 are linearly dependent, then I know y1 equals k times y2, right? So let's look at what the Ronskian would do. I just want to show you why this is true. I would have y1, y2, but I know y1 then, right, is k y2. So let's look at what the Ronskian would tell us. I would have k y2, y2. The derivative of that would just be k y2 primed, right? y2 primed. So look at if I cross these, I would get k y2 primed minus k y2 primed. So do you see why that equals 0 then if we have linearly dependent functions? Because if they can be written as constant multiples of each other, then when I take their derivatives, that's not going to change the derivative at all, and we're going to get that subtraction right here that'll get us to 0. I hope that makes sense. I can't see any confused looks right now. I'm imagining them, but I can't see any confused looks right now. Maybe you should take a break. I know we're at 25 minutes and I still have some more to go, people. So you might take a break, pause it, go get something to drink, non-alcoholic, and then come back. So let's look at an example here. So file, let me clear this really quick. Whoops. I haven't made a video in a while, so I'm kind of still rusty on all this stuff. So let's determine if linearly dependent. I'm being really lazy. Linearly independent, though. That noise outside of my office is ridiculous. So if I let's look at y1 being e to the x, y2 being e to the negative x. We've already shown that right isn't going to be linearly dependent, but let's just make sure the Ronskian shows us that. So the Ronskian is going to be e to the x, e to the negative x. Derivative of e to the x is e to the x. Derivative of e to the negative x is a negative e to the negative x. So again, I multiply these two. So what's that going to be? That's going to be a negative, well, when I multiply these, that's x minus x, which is 0. So that's a negative 1 minus, right? Now I multiply these two. That's e to the 0 also 1. So I get negative 2. That guy is clearly not 0. Therefore, we're linearly independent. Okay? Hope that makes sense. Let's see. Do I have another one that would be interesting? Sine and cosine we've kind of already showed. I don't know, let's try that one. y1 equals sine of 2x. I'm not sure what's going to happen. y2 equals sine of x cosine x. We might still need to use the identity, but I should get 0 here. So let's see what happens. So I'm going to get sine of 2x sine x cosine x, right? Derivative of sine of 2x is 2 cosine 2x, and here I get to do the product rule. So if I leave the, well, let's take the derivative of the first, that's cosine times cosine squared, or times cosine is cosine squared, then I get minus sine squared x. Okay, yeah, I think I'm gonna have to use some properties here. That's too bad. I was hoping I could show you this without having to use properties, but that's okay. So this guy right here, if you remember, is cosine of 2x. Okay, you remember that, right? And this guy right here, if you think this isn't actually sine of 2x, then it'd be 1/2 sine of 2x, because remember sine of 2x is 2 sine cosine. And then if we multiply these, let's see what we get. We get sine of 2x cosine of 2x minus, here this half and this 2 cancel. Sure enough, I get sine of 2x cosine of 2x. That's identically 0. Okay, that's 0 no matter what x values you put in. We're done. So these obviously are linearly dependent, which we already knew. All right, people. Oh my goodness. This is a lot of talking without anyone talking back to me. That's too bad, huh? All right, so what this all means then is that we have a theorem that we need. So I think this is, I should have been labeling these maybe. This is like theorem 4 or something. So this is the big deal. Let's let y1 and y2 be two linearly independent, okay, linearly independent solutions. Whoa. Solutions of the differential equation, right? Y double primed plus Py primed, where P and Q are functions of X. I'm just being lazy. And obviously P and Q continuous on some lovely interval. I don't know what interval that is. If capital Y of X is any solution, okay, any solution. This is the big deal, people, of this differential equation right here. This is a big deal. If we pick any solution, right, maybe it might have more than one. It definitely has more than one. Well, I shouldn't say that, but could have more than one. If y of x is any solution of this equation, then there exist two constants. We'll call them C1, C2. They live on I, such that I can write any solution, this solution y of x, as a linear combination of y1 and y2, meaning I can write that y as y2 c1y1 plus c2 y2. Again, a linear combination is just any multiples and adding them up. Okay, so this is the big deal here. So I mean, really the biggest thing about this is if I can find two linearly independent solutions of my differential equation, then I've found everything. Okay, that's what that is saying right there. When we have found two linearly independent solutions, then we have found all of the solutions. Let's write that down really quick. When we have found two linearly independent solutions, again, y2, because it's a second order, we have found all solutions. Okay. It's a pretty big deal. Pretty big deal. It's pretty cool. Okay. So therefore we call this y a general solution of the differential equation. All right, cool. So what we care about then, now I'm not going to prove that theorem for you. I want you to, not drop the class. It is proved in your book on page 107, and the proof is, it's pretty subtle, and not that you guys wouldn't understand it, but I'd rather talk about how are we going to actually solve these, which I'm sure is what you want to talk about too. So basically what we're going to deal with now is we're going to deal with specific differential equations, second order, where P and Q are just constants, and we're going to look at how do I find this y1 and this y2. Okay, let's do it. Let's do this. I'm sure people are wondering why I'm talking to myself in my office. Actually, that sometimes happens. Even when I'm not recording a lecture. All right. So I'm just making sure I'm not skipping anything in your book. Okay, so remember this chapter, we're gonna start talking about, well, some applied stuff, but also how do we solve second order differential equations. So the first type that we're going to look at with the linear second order differential equations are ones with constant coefficients. And then that's going to get us kind of set up for looking at the process. And then we'll look at, well, what if those coefficients are not constant? So what I'm talking about here is where that P and Q are constants. So in this case, we would have like a y double primed plus by primed plus cy. So this is a homogeneous second order linear differential equation constant coefficients, where a, b, and c are constants. And a is not 0, right? Because if a were 0, we wouldn't have a second order anymore. Okay. Your answers are going to involve e. That's just always going to be what's going to happen. So here's our argument, or our kind of derivation of how we find these solutions. Let's consider, why don't we? Let's do it. Let's consider y equals e to the rx, where r is just some number, okay? So if I consider y being, let's see if, what would this differential equation look like if this was my solution? So notice, okay, if y equals r to the x, y primed then is r e to the rx, and y double primed is r squared e to the rx. Remember, I just have to find two linear, whoops, man, it gets mad at me. Oh, stop it. I just have to find two linearly independent solutions, right? As long as I can find two linearly independent solutions, then I have found all the solutions. So what my goal is right now is to hope and pray to the math gods that my solutions look something like this, which we would maybe expect it to happen. Remember, e's derivative is itself, so I could probably mess with numbers enough to get this guy to be 0 if I had e raised to some multiple of x, okay? All right, so let's see what happens then. If I consider that solution, I'm gonna take the left-hand side of my differential equation, and I'm gonna plug and chug. So I'm going to put in a, I'm going to have that multiplied times r squared e to the rx, right? Then I have plus b times the first derivative, which is r e to the rx, and then plus c times e to the rx, okay? Now, this is so great, you guys. You're going to love this. I forgot how fun this was. Look at what I have in common to all of these here, right? So what I have then is ar squared plus br plus c times e to the rx. Remember, what I want to do is I want to find an r so that this is a solution. Okay, so I'm not verifying this as a solution. I want to find an r that makes this sucker a solution. So I am going to take this sucker and I'm going to set it equal to 0, okay? And if it is a solution, then I should be able to find an r that makes this statement, people, it makes this statement right here true. If this could be a solution, then I should be able to find an r that makes this true. And some of you have already seen it. This is so cool. The only way for this to be 0, right? E to the rx can never be 0. So I know that if I can find an r that makes this equation right here 0, then I know that I have found a solution. Isn't that neat? So look at this. This is a quadratic, okay? That means it has roots, 2 roots at the most. Well, we'll have 2 roots. You could have a repeated root. We'll talk about how to deal with that. But let's just say that these guys are distinct roots for right now. So let's put distinct, meaning they're not the same. Distinct roots, let's say R1 and R2. Then look at what we have. I have 2 solutions then. I have e to the R1x, and I have y sub 2 equals e to the r sub 2x, because each of these r's make this whole thing 0, which would make this whole thing 0, which would make this guy a solution. So my general solution then, or a general solution, right, would be c1 e to the r1x plus c2 e to the r2x. This is a general solution. Isn't that neat? It's so easy. It's so pretty. That's it, people. Let's do some examples. Obviously. Whoops. Okay, so for example, let's look back at that problem that we've done like 3 times already. So I have y double primed minus y equals 0. So let me put this layer. I know that looks a little bit crazy, but notice, well, let's take that one off. Okay, so how are we going to do this, right? Well, what I need to think about is I'm going to have ar squared br and then plus c. So what you want to remember is that this y right here basically corresponds to r to the 0. This y prime basically corresponds to r to the 1, and this corresponds to r squared if you want to remember what your coefficients are, because you got to be a little bit careful to not let that y become an r. So what would I get here basically? I would get r, whoops, I understand. And this is what we call our characteristic equation. Oh, we should put that. Oh, people, we need to put this in your notes. This guy right here. Oh my goodness. This guy right here is what we call our characteristic equation. It characterizes what type of solutions we're going to have, okay? So that is what we call our characteristic equation. We're not writing this down. This is a theorem in your book. It's Theorem 5. You're welcome to write this down, but I'm getting kind of tired of talking. So I'll let you do that on your own. All right, so our characteristic equation then, what is our characteristic equation going to be? Well, what are my coefficients? There's a 1 right here and a -1 right here. So I'm going to have 1 times r squared, also known as r squared, minus 1 times r, which is r. I'm going to set this equal to 0. Let's see, I can factor this. We're back to beginning algebra. So what are our roots? 0 and 1. So that means y sub 1. Did I get that right? Equals 0. Oh, I just did what I told you not to do, people. Look at that. I did that on purpose. Guys, I did that on purpose. How did I know I was wrong? Because we did this equation already. We know our solution should be e to the x and e to the negative x. I'm sorry. So this is r squared minus 1 equals 0, which means r squared equals 1. Remember, plus or minus. So what does r equal? Plus or minus 1. So y sub 1 would be e to the 1x. Y sub 2 would be e to the negative x, or negative 1x. And what is my general solution, or what is a general solution then to this equation? C1 e to C1 e to the x plus C2 e to the negative x, which we already showed was true. We know that. Let's do another one of these really quick. What about 4y double prime minus y primed minus 3y equals 0. So again, what is my characteristic equation here then? This one's a little easier to see. We get 4r squared minus r minus 3 equals 0. You people who don't like to factor need to get over it and figure out how to factor. You should not have to use the quadratic formula for this. I guess not that it's wrong. I can't like stop you from using it. But come on, look at how much easier that is, right? So what do we have for our roots? -3/4 and 1. And so we have two solutions here. We have y sub 1 is e to the -3/4 x. Y sub 2 is e to the x. And so our general solution then, y, is C1 e to the -3/4 x plus C2 e to the x. Isn't that cool? I love it. Isn't that great? It's good stuff. As my dad used to say, it's good stuff, Maynard. Right? All right, so that's pretty neat. I like that. Those are really fun to do. So the question now, I am almost done lecturing. Thank goodness for both of us, right? Is look at what I had here. I had, oh my goodness. These two were distinct, meaning they weren't the same, but we know that quadratics can have up to 2 distinct roots, right? We could have a repeated root. So what we want to look at right now is, what should we do if we have a repeated root? What would our general solution kind of look like, okay? So what I want to consider then is let's consider, wow, that was amazing. That was amazing. Did you see that? That was really, really cool. Okay, so let's consider, I messed up the brush size here. Consider the repeated root of the repeated root of the characteristic equation. And let's just say that repeated root then, let's just call it r sub 1, okay? So what we would have had then is r minus r sub 1 quantity squared equals 0. This is how I get a repeated root if it factors into a perfect binomial. So if that's true, let's FOIL this out really quick. This would be r squared minus 2r1r, right? Plus r sub 1 squared equals 0. So let's bring that back then. What would this be then in terms of my differential equation? I would have y double primed minus 2r1y, right? Plus r1 squared, I'm sorry, this is y primed, y equals 0. Okay, so this r sub 1 must be the solution, or not the solution, but have come from the characteristic equation for this differential equation right here. So here's what we're going to do. We are actually going to pick a solution that is linearly independent. So one of the solutions obviously is going to be e to the r1x. The other solution, now I'm not gonna, if we were in class, I would I would verify this for you, but we're not in class and I've been talking for 45 minutes straight without a break. So I don't want to talk anymore. You probably don't want to listen to me anymore. But the other solution we're going to pick is, remember, I just need a solution that is linearly independent of this, meaning it should not be, right, a constant multiple of this guy. Well, you know what's not a constant multiple of this guy? Just x times this guy, because x is a variable. I would like you to please go and verify. So this is going to be on you, people. You need to take this guy and you need to verify it's a solution for this, right? You need to verify that it's a solution to this. And I want to see that on your homework. So I hope you guys listen to the end of this. So for your homework, for 2.1, this is part of your homework. You need to verify that this x e to the r1x is a solution to this differential equation right here. Y double prime minus 2r1y primed plus r1 squared y, okay? I want to see that in your homework. If it's not in your homework, you won't get full credit. Okay, so now that we've found two linearly independent solutions, what is a general solution of an equation with a repeated root? It is going to be c1 e to the r1x plus c2x e to the r1x. Again, you want to think of it as throwing that x in there to make these two linearly independent. If you want, you can factor out, right? You can factor out that e to the r sub 1x. You don't have to, though. I don't care how you put that. Either way. All right, let's do one example and then I'm done. I'm done talking. It does happen. Isn't it amazing? All right, so here's what we got. Let's solve this. Ooh, let's do, this is an initial value problem. This will be fun. Y primed plus 9y equals 0, where y of 0 equals -1, and y primed of 0 equals 2. Okay, so what's our characteristic equation here? It's r squared minus 6r plus 9 equals 0. So this, as you see, is a repeated root. Okay, so my general solution then, sometimes I'll put 3 just to remind myself. So my general solution then is c1 e to the 3x plus c2x e to the 3x. Okay, linearly independent solutions. Now, how do I find my c1 and c2? Well, I'm going to need y primed, right? That is going to be 3c1 e to the 3x. I'm going to do product rule here, plus c2 e to the 3x plus 3c2x e to the 3x. So let's start plugging in that 0. So y of 0 then, if I plug that in here, this is pretty cool. It just gives me c1. When I put in 0 here, that goes to 0. So I know c1 then is -1. When I take y primed of 0, I'm going to get 3c1 plus c2. That guy's 0 equals 2. So with this c1 being -3, if I plug that in here, guys, I'm doing arithmetic all by myself. I think c2 equals 5. Oh no, you guys. Yeah, I think so. I'm pretty confident. I'm fairly confident in that. So what is my particular solution that wants to go through the point 0, -1 and have slope at 0 of 2? I would have a negative e to the 3x, right, plus 5x e to the 3x. If you cannot go to sleep at night without factoring out a common term, no, it doesn't matter. I'm going to put it after, and I don't like a negative first, so I would put this as like 5x minus 1. I might be one of those people, times e to the 3x. Oh, you guys. If you're still with me and if you didn't take a break, you're amazing. You should have taken a break. That was 50 minutes of loveliness, and I just, ignored any advice about lecturing, doing online lectures in small chunks. So don't forget to add that little problem to your homework, verifying, again, what was it that I want you to do? I want you to verify, right, that this x e to the r1x is a solution to this second order linear differential equation. Homework is due Thursday, so if you have questions, please let me know. And Thursday, we will, in class on Thursday, do the fun sheet together. It's also posted on Canvas. So we'll do a little bit of this at the beginning, but we really cannot lose too much class time just because I had to miss that day. So feel free to email me questions if you have questions. Come to my office hours. If my office hours don't work for you, send me an email and we will get together. All right, you guys, have a great day. I'll see you on Thursday.